What?
So Felix, you can start.
Great. Okay. So, hello everybody. So today I tried to explain Gromov non-squeezing theorem, and essentially the goal is to tell why holomorphic curves are so useful in order to understand symplectic embedding problems. And this proof is a kind of a model for any other proof. Also for this later in the evening, we do something with phleuromology, and this idea of Gromov to use symplectic, in symplectic problems, holomorphic curves, is totally fundamental for for most, not so easy results in symplectic geometry, and in particular for when you want to have obstructions for embedding problems, you best work with J-holomorphic curves. So I mostly illustrated by giving an idea of the proof of Gromov's theorem, because it's if you understand this, you can essentially at least follow the main ideas of any other proof of that kind, right? Okay, so the statement is this. We take, as yesterday, a ball of a given size, pi times radius square is A, and we try to embedding into a much bigger set a priori. So you see, this is a cylinder, like in the picture, right? So here in this picture, can you see that? So the cylinder is the volume of the cylinder is infinite dimensional, right? I take this cross, for instance, if n is 2, a complex plane. So with the usual symplectic structure. So the volume is infinite dimensional, and I try to embed a ball as big as possible in a symplectic way into this cylinder. Okay? So Gromov says the identity is already the best thing ever. You cannot do better than the identity mapping. When you do epsilon bigger, you would maybe try to a bit squeeze, right? Push a bit. And what happens is double. Of course, you can easily move this point in by a Hamiltonian isotropy. This is very elementary. But what happens is on your side, somebody comes out. So double, right? You push here, you push here, you push here, but other points must come out. It's unavoidable. And well, when you try, you don't succeed. But the point is, the set of candidates in order to do it is infinite dimensional Lie group, and you have to show that nobody can do the job, right? You need a kind of a good, heavy obstruction. And Gromov found that this theorem can be proved by nowadays about 6 different methods, but Gromov's method is maybe the most important for other developments. So I want to do it with his holomorphic curves. So the statement again is identity is already the best map. You cannot do better. Fine. A statement. So this we want to prove today. Okay. So, sorry, here the light is probably worse. So we would have to have fixed nails on the ceiling. Cannot destroy this cool here. Okay, so this is an important, 2 easy but relevant exercises. The first one is, if you would look at volume preserving embeddings into, let's say here, you fix the disk to be size 1, then you can put an arbitrary big ball into it, even the whole R2N. And it's very easy. This we have actually already done yesterday. Right? With this band thing. You take here one plane and you can do it into a thin band, and then you can, well, then you can do something. So this is easy. So it means that the Gromov theorem is extremely symplectic phenomenon and not about volume preserving or ergodic theory something. It's Hamiltonian dynamics and symplectic geometry. And the second exercise that is also important, in Gromov theorem, the splitting here is in the complex planes. So it's symplectic splitting, or if you want to say in C and Cn minus 1. If you would take Lagrangian splitting, it's totally wrong. You can very easily embed a ball as large as you like. And even by a linear mapping, even by a diagonal mapping. It's very easy. Okay? So the splitting here is very important. It must be complex splitting in the theorem. Very good. So now let's start the proof. Question? Oh, I don't hear.
I'm sorry. So, Felix, could you please briefly recall what is Lagrangian splitting? Because somebody joined us.
It would just mean it would just mean here Q1, Q2, and then here the rest, like, you know, Q3, Qn, P1, Pn. So this would be a Lagrangian splitting here, that you take, yeah. So when you do it this way, you can do everything in, and what in Gromov is meant here, Q1, P1, and here Qi, Pi for the higher ones. Complex splitting, right? When you identify the R2s with Qi, Pi coordinates as complex planes.
Okay, so you change the symplectic structure in the image. That's it.
No. Well, that would be a way to say that you do the same but change the symplectic structure. Mm-hmm. Okay. Or you take the same symplectic structure, but look not at this cylinder, but at this cylinder, not at this, but at this, or something like this, right? Okay.
Thank you. Yes.
As you like. Mm-hmm. Yes. Good. Mm-hmm. Okay, now we start a proof. So first I have to tell you what a holomorphic curve is. Probably you know, so I already wrote that down. We first do it with image in Cn or in R2n. It's a bit easier, but then it can also be in all symplectic manifolds, and today it would be enough in Cn, but later we also need it in Cpn or in S2 cross S2, so it's a bit better to say what a holomorphic or an almost holomorphic curve in a symplectic manifold is. But first let's do it in Cn. So it's just a map from a Riemann surface into an almost complex manifold where the almost complex structure is adapted to the symplectic structure. So here I want to say what a holomorphic curve is, a J-holomorphic curve. So we have a Riemann surface as a domain, and you fix a conformal structure. It just means you decide, yeah, you somehow decide what 90 degrees are, right? In every point in the tangent plane, you decide what it means by turning by 90 degrees, or you decide what it means to turn such that if you apply twice, it's minus the identity. Yeah, you know what it means. It's a conformal structure, okay? And it's a fact that saying this is the same thing as to put a holomorphic atlas on the Riemann surface, right? Everything is integrable in dimension 2, so it's actually the same as just a complex line or any a Riemann surface. These are our domains, and in our applications it will always be spheres actually. It's enough to have here just a sphere, and in every point you can take for all these things actually the usual complex structure on the sphere. It would be enough, Not very conceptual, but for our talks, it's enough. Okay, good. And now the main idea is, you see, in Riemannian geometry, many proofs go like this. You test your Riemannian structure by geodesics, by the locally shortest connections. And so here in complex geometry, you kind of take complex geodesics, and they are the holomorphic curves. And with these, you can prove many things. And it turns out that in symplectic geometry, even though you don't have a priori canonical complex structure, you still have complex structures, and you can use them to study holomorphic curves, and with them you can prove something, and then it does not depend on the choice of the almost complex structure. So it's an auxiliary tool, right? We will have a symplectic manifold M omega. We will choose a J that is kind of related to omega, and then we study holomorphic curves for that J, and from the set of such holomorphic curves, we get results about the symplectic manifold that we started from. That's the idea. The J is auxiliary, but very useful. Okay? Good. So now I have to start writing. Good. So this is our today goal. Yeah. So what is now a holomorphic curve? Yeah. So what is a holomorphic curve? It's just a map U from such a sigma into Cn first, such that, you know, U commutes with the i's. So here we have the conformal structure, and here we have the usual J0. And this is bad. So what we want is that, so this is this is holomorphic. Is holomorphic. By definition, if first you turn and then you differentiate, is the same as first you go with the differential and then you turn. So the differential of the map is compatible with the two complex structures, right? Here we have a conformal structure, and here we have the usual complex structure, and this is a holomorphic mapping. Okay?
And so G0 is the operator of multiplication by I, yes?
This is just as yesterday, it's I plus I for now. Hmm? So again, geometrically, maybe just means that you have, for instance, a sphere. You have a sphere. You have a point, and you look at the point. Here you have the mapping U, and then you have here your manifold, which is here Cn, and then you maybe look at the image of this thing here, which is a sphere, kind of. And then what it means is that you can either first look what happens to the vector and look at the image curve, so du at x of v, and then you turn it, and then you stay tangent to the image, or you could also first turn it, I, v, and then map it. And it gives the same, right? Yeah, you understand. It's the usual compatibility, and this is a holomorphic map or a complex curve. And what I wish to say is that, so from an analytic point of view, later we will have to kind of study the set of solutions of this. So for this, it's important to know what kind of an equation it is. So it's, of course, a PDE, but it is linear in U. When you have two, you can add, it's linear, and it's elliptic, right? So for now, there are two good things. It's linear and it's elliptic. Elliptic will mean that there are very good regularity properties, and there will also be very good compactness properties. And if it would not be elliptic, you could just go home. It's very hard to do modularly problems with non-elliptic systems, but this is a Cauchy-Riemann equation, and it's linear and elliptic. Okay, good. Not that I know, but I think this is true this way to say. Okay, now we can do exactly the same if we have here a manifold with an almost complex structure, which just means that an endomorphism on the tangent bundle J, such that J is minus identity. Okay, so do the same, or can do the same for a manifold with an almost complex structure. You cannot read it, but it means almost complex structure. And well, so this is what? This is just an endomorphism of the tangent bundle Tm, such that J square is minus identity. So why is it called almost complex? Now, it's not a complex structure. It does not come from a holomorphic atlas in general. It's not integrable, maybe.
Could you please move to the bottom?
Oh.
Yes, thank you. Yes. Yes.
You see?
Yes.
The story was actually like this. Gromov wanted to prove something about Kähler manifolds. And in Kähler manifolds, the J's are a kind of the best. They are given, they come with the Kähler metric. And they are also wonderful because they are integrable in the sense that they come from a holomorphic atlas, right? You can take an atlas from Cn to the Kähler manifold so that the usual J0 on Cn is exactly via the atlas the J you have in the manifold. And Gromov tried to prove something in Kähler geometry and it didn't work. And then he relaxed to symplectic, but then he had to relax the notion of the J's because not all symplectic manifolds carry integrable J's. But when you just want to have that J's minus identity, you can still study maps U so that the differential commutes with the I here and the J in the manifold. It makes sense. And this equation, so again, you ask for U's, but now into the manifold M, so that, well, this holds. But now it's this J. Can you read it? Maybe I don't repeat everything. It's
just like this.
Right? You just look at this. So now this is not linear anymore because U plus another U doesn't make sense. But it's not so important. But it's still elliptic. It's called quasi-linear. It's kind of almost linear. Well, what goes wrong is just a bit, the tangent plane goes a bit away, but it's not so important. So it's a bit like this. For a geometer, he's shocked because he has to study PDE. But for somebody in analysis, when you ask him, he says, yeah, that's ridiculous. It's the easiest thing he has ever seen because for all analytic properties, whether it was just a Gauss-Riemann or whether it's like now this nonlinear thing, doesn't matter. The difference is from the linear, there are lower order terms, and for the analysis, they do not play a role. Okay? So it's as good as you can think. It's almost linear kind of, and it's still elliptic, and this will be very useful. And you want to study the space of solutions of this problem. Maybe when you say that a given point has to go to a given point, you can add certain conditions. We will see that. Okay?
So, Felix, so just to recall for beginners, elliptic means that the main symbol is has a zero kernel. Yes.
Exactly.
Yes.
Mm-hmm. Mm-hmm. Yeah. And for instance, this can be used to show that if you have a weak solution, it's actually automatically smooth. Right? You can prove existence thing in certain suborder spaces and use functional analysis, and then by ellipticity, it comes from for free that what you find is actually smooth and classical. So this would not be true for hyperbolic or parabolic in general. And also certain compactness properties will come. Okay. So in order to make this idea work, you should maybe first check that every symplectic manifold has an almost complex structure. We will not use it much, but let's say it's very easy. So lemma for all m omega, there is almost complex structure. J on n, maybe on Tn. So this is in general not true, right? I mean, for instance, to have such a J, you need even dimension, but even that will not be true. But if you are a symplectic manifold, you can always find a J. So now there will be remarks later on. It's not useful. You see, there is now no canonical J, but you kind of don't care. You just take all of them. You take the class of all such J's. But when you take all of them, certain things do not work. So you should restrict yourself to J's that are well related to omega, because that's what you have. And there are two choices. My choice today will be, I didn't decide. So I will take all those. These are all J's such that omega of U, J, U is positive for all non-zero u. So what it means is that if I take a vector and I take the complex line spanned by this vector, so the pair u, ju. So this is a complex line, right? A one-dimensional complex subvector space in T, X, M. I want that omega on this oriented complex line is positive. So these J's are called omega tame. And this is a condition we will use. Otherwise, you do not get compactness statements for solution spaces as we will need it. Okay? So this is the minimal requirement necessary in symplectic geometry. You could ask more. In 3 hours in the Floer theory thing, you would ask more. You would ask that you know, omega j u v defines a Riemannian metric. So that for every pair u v.
No. J should be at the same place in both.
You want it on the other side. You can always take minus j's.
The two should agree, the two definitions.
Ah, that's very bad. I didn't prepare. That's true. Okay, thank you. So this is the second choice, that you say that J and omega together produce a Riemannian metric. So this is what happens, of course, in the Kähler situation. But for today, this is not our choice. For today, it's this. This is enough, and it's a bit a bigger class. So the crucial thing is to observe that these two spaces are not empty and contractible. They contain no topology. And what it means is that whatever you do at the end will not depend on the specific choice of the J you work with. You can, the contractibility of this space is used to show that when you define invariance with a given J, the invariant will not depend on the choice. Something like this. Okay? So now maybe before we go on, I want to give an indication why it is a good idea to look at J's, at holomorphic almost complex structure, in order to do something about symplectic manifolds. And of course, we could just go on with the proof and then we see, but I want to make anyway 2 a priori remarks. So why is it useful to look at J's? So one thing one can kind of guess. So one remark is that, you see, yesterday, we have already seen that the Hamiltonian vector field of a Hamiltonian function can be written as J times gradient. And if I would take the second choice of J's, the compatible ones, this would still be true for the gradient defined with respect to the Riemannian metric defined by omega and J, which is very good in Floer theory, very useful. So this is kind of an indication that holomorphic things may be useful in Hamiltonian dynamics and symplectic geometry. And the second thing is a bit more important today. So you see, now that we have omega and J, and maybe also a Riemannian metric, when we assume the things compatible, we have 2 notions of area, and we can compare them. Maybe I have to switch. Wait. Okay. Yeah, here is a huge, it's very light. But tomorrow the weather will get worse. Promised. So the second motivation is about areas. So let's compare the omega area. Let's go back to Cn to fix the ideas. So then we have J0, right? The usual complex structure. We have omega 0, and we have the usual Euclidean metric. And now if we have a little piece of a surface, we can either evaluate omega over it, or we can take its usual Riemannian measure by restricting the Euclidean measure to the surface and take the remaining measure. Okay, so we compare the area with respect to the symplectic structure with the area with respect to the Euclidean structure. And so what is this? Well, here, I mean, here you know what it is, and here the area.
No, we cannot yet see it. Can you? Yeah, right. That's enough, a bit less. Okay. Fine. Yeah, like this. Okay.
So this is just when I have a piece of surface or maybe a real sphere or something. This is just the integral, right? Everything the sigmas are oriented. Okay, so the outcome is the following. Then this is easy. The area, the omega thing, is always less. And equality you have if and only if sigma is holomorphic. Okay, so this is an indication kind of that the J-holomorphic curves in the symplectic world are maybe kind of specially good because they are exactly those where the two natural notions of area coincide. And this fact we will actually use in Gromov squeezing theory. That's why I want to tell. And the proof is only Cauchy-Schwarz. The proof is just that if I take any pair of vectors, nothing to do a priori with being tangent to sigma or not, well, it's true that so I do not yet integrate. By definition, it's compatible. Well, sorry, it's in the wrong slot.
Maybe a bit lower.
Okay, but you forgive me.
No. I mean on the whiteboard. On the whiteboard, you write it just a bit lower than this.
Even lower.
No.
Okay.
Don't shift. No, don't shift the. Yeah, right. A bit.
Okay.
Yeah, I mean the beginning was okay, but J naught was. Oh, okay, that's fine.
So U is not the man. Okay. So you put it somewhere. I don't know.
What is gamma? Sorry, is it a gamma in front?
This is omega 0.
And in front of it, what is it?
Proof. Proof.
Sorry.
So by Cauchy-Schwarz is less than this. Which is exactly and this is always true. Okay, I don't want to be complete, but now you just discuss case of inequality along a rim surface, and you find this. So this is now proven. When you integrate, you find the lesser equal, and the inequality you easily see from discussing equality case. Must be parallel, and then you get it. Okay. So this is a linear algebra indication that holomorphic curves are maybe useful because special in symplectic manifolds, at least if the almost complex structure is compatible. Okay? Okay, now we discussed the proof. We can start the proof. Great. There is black. Okay, now comes the proof of Gromov squeezing. Okay, so we don't know much, right? It's actually very little we know. What is given? Given is our symplectic embedding. Our disk. And all we know is the symplecticity. So phi pullback of omega is omega. Okay, so this we know. So for somewhat strange didactical reasons, I will first discuss a special case that later will turn out to be ridiculous, but I think it's good to start this way. So first, you understand, we are given extremely little information because being symplectic is such a weak condition. So now I first assume something in addition, namely, first, I also assume that phi does not only preserve omega 0, but also j. Okay, so just in order to motivate my proof. Okay, good. You see, maybe I can already say now that this is ridiculous because if a local diffeomorphism preserves omega 0 and j0, it's a Kähler map. And the Kähler map for Euclidean metric is actually by rigidity for these maps, easy to see, is actually a Euclidean isometry. So the ball can only be translated. So then the theorem is obvious. But I want to overlook this and just first think of how I found a proof in this additional set, in this special setting. Okay? So now the key point is to make a picture. Okay, let me write one line and then I start the picture. So what we do is we consider in the image cylinder the flat disk through the image point of the center, right? We consider the disk I call it the disk of size A through the point Z0, and where Z0 is the image of the center. So this is a main idea of this proof. Okay, wait a second. Okay, now comes a very important picture. Like this. So here is my ball. Here is 0, and here is my embedding, and here is my cylinder. Can you see that?
See that. Yeah.
Can you see it? So what do? We take the image point, phi of 0, it's somewhere. I don't know where it is. It's not here at 0, somewhere here. Okay, and then I take the flat disk. Here is so this point has a coordinate Z0 and another coordinate over in D2. And then I take the disk there. So this is the usual disk in the cylinder at this point. Okay? And now, so my image is something, I didn't say. Right? So the image of my full ball here intersects this disk somewhere. Looks maybe like this. So this set it's the image of the ball intersected with this disk. Can you see that?
Not very well. It's a bit fuzzy. Yeah, kind of.
So what
Say
do
it
we
again. What's going on here? Can you repeat it?
Oh, I repeat. Okay, so I have my ball. I take the center. I look where it goes. Ah, U is phi, sorry. This is our symplectic embedding. And it goes somewhere. And phi of u has a coordinate in the disk and a coordinate in the Cn minus 1. And I take this coordinate. And then I take the disk at this level. So this is the, it should have a name. It's the disk at Z0 of size A. And this disk I intersect with the image of my ball, right? This is a certain subset of this disk. The red, where by definition, I intersect the image of my ball with this flat blue disk. It's maybe not connected. It may not be connected, but it contains phi of 0. Okay? But now comes the key point. Now we look at the red thing here. So we look at the preimage, and it looks somehow like this. Yeah, actually, it needs not to be connected, but I don't want to make crazy things. So this is a certain surface, S. And what we know two things. We know it contains the origin, and it's also properly embedded. It goes out to the boundary because the image was strictly in. I maybe didn't say that. Maybe I want to map the closed ball, but it's not important.
I'm not sure everybody knows what is properly embedded.
Yeah, maybe we forget it. You just should believe me that the image goes out to the boundary. It doesn't get stuck inside. It really goes out because you see the image here was really in the cylinder. So if I take the preimage of the full disk, it really goes out to the boundary because the image was really inside. Maybe you can thicken. You take d2 of a plus epsilon, then it's clear, and it would be good enough for the proof.
But I think properly embedded means a submanifold, yes?
No, it means that the preimage of compact sets is compact. Maybe, yeah, that it means. But if we work, it's better. Sorry, let's forget about the proper thing. Well, just let's say that phi is defined on the closed ball. Or, yeah, that would be, it's a technical point that will not help anything. The key thing is to look at this S. So what is it? It's by definition the preimage of the red thing, of this red thing.
No, this won't be visible, sorry. It's exactly the wrong spot to write a formula.
Oh, so bad, then I will move it.
A bit below. Oh,
Can you see
right,
it?
right. Yes. Fine.
So it's the formula is not important. The key is that you look at the preimage of the red thing and call it S and analyze it. Okay? So what is it? It's something that goes, it's a surface because, well, at least locally, because phi is a diffeomorphism. It goes through the origin, and the key thing is it's J0 holomorphic. Because phi, by my assumption, preserved J0, and this, you see, this here, this blue thing is of course a J holomorphic disk because it's flat, and the holomorphic structure is split. So the blue thing is holomorphic. Since this surface piece is a subset, it's holomorphic. And when I take the preimage, it's also holomorphic because phi preserved J. Okay? So maybe I just want to say that, so this thing is a complex submanifold of the ball through the origin. It's a complex, real two-dimensional submanifold of the ball through zero. That's what it is, and that's enough to know for us. Fine with you? Okay, wait a sec. Are you happy? Did you believe that? No. Okay, so what do you know about complex submanifolds of a ball in Cn? Yeah, there is something very classical. It's called Le Long inequality, or something like monotonicity formula for minimal surfaces. Because you see such a holomorphic curve in Cn is actually exactly the same as a minimal surface. So these things. So what is the statement? It's called Le Long inequality. It says the following. I make a sketch picture. So among all these, each of these has area. I mean Euclidean area, bigger or equal. Sorry. What?
What's in the picture?
So this is kind of our thing. It's a formal picture. This one has area at least this. That's the law inequality. You see, in high dimensions, it's not clear because it could be like this. Such a thing has area much smaller than such a thing. In high dimensions, you can find such embedded disks with arbitrary small area, right? But they cannot be holomorphic. So Le Long says that the area of our S is at least A. So there are various proofs. You invented his own in general, but it is also classical for balls, but for analytes it's different. Good. So now the proof is done under this ridiculous additional assumption. Because, so what do we have? We have that the A is like, this was this Le Long. But then, from what we saw above, is that since it was J holomorphic, it is actually equal to the other area. You remember, This is the hard inequality, but we used that it was J0 holomorphic. But I rewrite that. So this is just the integral over this S of omega 0. But now I use that phi is symplectic. Right? So now I do coordinate change. Can one still see?
Mm-hmm.
Okay, but then we know that phi of S is in this disk. Right, through the point. Yeah, but this is of course A. And that's it. Right, so A is less than A. That is Gromov theorem. Okay, so now, as I said before, this proof is ridiculous because we assumed that phi preserves not only omega 0, but also J0. And these together, yeah, by elementary means that is a translation, and then the theorem is clear. So in a way, we want to change that proof so that it still works without the assumption that phi preserves J, but only assuming it preserves omega. Do you agree? Alexei? Alexei has gone.
Yeah, yes,
He's
yes.
abstaining.
Yes,
What?
It's okay.
Are you happy?
Yeah, yes, yes, it's okay.
So this proof was absurd, but it tells us exactly what we should do. So in the new proof, we will have the good J in the domain, and in the image, well, we have no J given at all. And we will simply do the following. We will simply push forward. We will simply choose on the image, on the cylinder, a J such that on the image of our ball, it is the push forward of the J of the domain. And then we extend it. And for that J, we will also find this flat disk, which is J, but really J holomorphic. But it's not flat anymore. And if we have that disk, we are done. We repeat exactly what we have done now. But to find that disk, which in this Mickey Mouse proof is ridiculous because it's a flat disk, is very difficult. But if we find such a disk through the point phi of 0, the proof is the same. Okay? So the strategy is to try, I repeat, we want to do exactly the same, but under the hypothesis that here we do not have J0, but we take here the usual I, and then on the image here of the ball, we take a J that is just a push forward of I. Well, of this J0 maybe. Okay, and then we extend it to the whole cylinder. And this can always be done just because the space of good J's is contractible. You can always extend. You can do partition of unity, kind of. Okay, good. So now this picture, maybe you should just memorize it. We just do the same thing, but with the J here, an extension of the push forward. And then we try to find through this point, maybe not a flat disk, but somehow a disk. And if you can do that, everything is the same. Okay, so now comes the real proof. So the real proof. So we now assume that phi is only symplectic. Nothing else, right? And I repeat, we choose the J, I call it J phi, an almost complex structure on the cylinder. So this is my notation for the cylinder. The ball crossed the disk. Well, this is as a such that is the push forward. Yeah. Right? On the image, we want that phi is J holomorphic. Yeah, but not for the usual J, but for this strange J. And then this strange J, we extend to the whole cylinder somehow, so that we still have tailness. Tail. Okay? And all we have to find is an embedded, should be embedded. Through phi of 0. And somehow it should go to the boundary, right? So it's something like this. Here is the image. And through the center, you want to find in somehow a disk. But it should go out. When you find this, you are done. So well, you just believe it. When you have this, you just repeat the proof of before. Okay? So now something historically really very strange happens. So finding disks is actually a bit difficult because these holomorphic maps are much easier in this setting if they have no boundary. So Gromov fished for spheres. But something like 5 years ago, 2 Russian, one of them is in Toulouse, and I've of course forgotten, they actually proved that you can also do it for disks. But this boundary condition is a bit ugly because the boundary condition, if it's not linear, but here it's on a circle, the Fredholm problem they have to look at is very ugly. So what they do, they first change from the disk to the triangle, and then they work on a piecewise linear boundary condition on the triangle, and then they find triangle with boundary on the boundary of the cylinder also becomes a triangle cross Cn-1, and then it kind of works. But yeah, but we will not do, it's maybe somehow for a man from analysis, it may be easier, but Gromov went for spheres. It's a little bit better. So it's better to work with closed holomorphic domains, I mean curves. So the first thing Gromov does is he doesn't take disk cross Cn-1, he takes sphere cross Cn-1. Just he compactifies the sphere by adding 1 point. You actually have to take a little annulus, but let's forget that, right? So let's just observe that the cylinder compactifies to S2 of A cross Cn-1. So we don't have here these flat disks, but we have the flat spheres, and we want to find, well, we have our phi of 0 here in somewhere, and in the homology class of this sphere, the only non-trivial one, we want to find the J phi we actually also extend. It's also easy. We want to find a J phi holomorphic sphere going through the point phi of 0. And And then we can also repeat the proof. It's a bit better to have domains that are spheres, not disks. Okay? So now we want to find is a J-phi holomorphic sphere. In class, it should actually be embedded. Well, I call that C. It's the homology class of S2 cross a point for is a 0. And it should also go through phi of 0. Can one read it?
But why is it necessary to have it embedded?
Well, it will, maybe not, but it will come out for free by a junction, But maybe it's not necessary. I didn't check. Maybe immersed. When we do the integral transformation, maybe we should have at least immersed. Or I didn't check. Maybe it goes the wrong way around. Yeah, I should think we should go through the previous inequalities.
Well, singularities are rare, and outside of them, it's an immersion.
Probably it's okay. So here, if this is not a diffeomorphism, you have to say that you mean it with multiplicity, and probably it's still okay. Should check. But it will come out embedded because it's a minimal class, and yeah. Okay.
Well, this is an extra theorem, anyway.
It's true, it's an extra theorem. Yeah, but you know,
okay.
We use them all. Yeah, no, it's true. Right. Maybe it's a good point. Maybe one should keep minimal. So UL says one can do it even easier. I think it's true. Good. Okay. So now comes a crucial idea of Gromov. So we have a J that we really do not understand because we don't know anything about phi. So therefore we only know it's symplectic. It can be totally wild. And therefore we don't know really anything about phi push forward of J. So our J phi on the target S2 cross Cn minus 1, we only know that it is a tame, almost complex structure for the symplectic form. We know extremely little. So the key idea of Gromov is to say, if this problem of finding this holomorphic sphere in a given homology class, if it had been the usual J, you know exactly. There is exactly one solution. And his idea is to say, this property survives. Maybe not one, but at least one. So there is something like a continuation argument for this PD. If you change the J, you have some control on the space of solutions if you know one of them very well, right? Okay, so maybe I say that. So a very obvious observation is that, note that this doesn't write. So note that for the usual J0, there is a unique such sphere, right? It's just, well, we have, I mean, before the picture was like this, but now this is more like a sphere. And we have just, the solution is just, the sphere, well, at phi of 0, right? The sphere going through this point, phi of 0. The compactification of this disk, the flat sphere, this is a solution. And up to reparameterization, when you only look at the image, it's the only solution by maximum principle. There is no other solution. So there is a solution and it's unique. There is exactly one solution. So this, okay. So now Gromov says, let's take since we know that the space of almost complex structure is connected, let's take a path from this good J to our unknown J, and let's see what happens with the solutions if we vary the J. Okay? So he chooses a path JT, T in 0, 1, okay, from the good one to this extension. And for every T, you try to understand how many spheres there are through the point phi of 0. JT holomorphic spheres, right? So these are all almost complex structures. Well, and they're actually omega tame. They are good, right? Okay, so for each fixed T in 0, 1, for each T, you look at the space of solutions. We call that moduli space. So this is space of solutions. The space or the set of JT holomorphic spheres, well, in that class, through that point, through phi of 0. Right, somehow we have here this phi of 0. And for the beginning one, it's this flat, the flat disk, and for another one, it may be something like a difficult sphere, or maybe there are 5 of them, or maybe there is a one-dimensional family. We don't know, but that's what Gromov looks at. So now the whole thing starts. So you have a moduli problem, and you want to understand this moduli space. And there are many things to do. So maybe I write down some letter. So what you actually do is you look at 2 different kind of spaces. First, you look at this MT, so the space of such spheres in this class through that point for a fixed T. And then you also take the universal moduli space, the union of all these MT, right? So you also look at here the universal, also look at this M, which is the union, the disjoint union. Okay, so maybe you can believe that for fixed T, it's a 0-dimensional manifold. It's actually not true, only for a generic, but okay, a bit naively. Because it was true for J0, and some Fredholm theory tells you that for good J's, it's also true. I don't do anything about that, you just believe it. It's for good J's, for fixed T, a 0-dimensional manifold. So then you can probably believe that this thing, with some luck, is a 1-dimensional manifold. Because it's a, okay? And this is true. But for this, you need some genericity for your path. And also something to check for the start point and the end point. For the start point, we have no choice. And for the end point, we could work a bit on the extension, actually, outside of the ball. We could wiggle there to make it true. So, fact, for most path, for generic path, this is a 1-dimensional manifold. So it's a manifold and it has dimension 1. So this is not so difficult if you are used to the machinery. This could have done before. So you need Fredholm theory, and you have to build some bundles and some Fredholm sections. And the dimension 1 just comes from the Fredholm index of the Cauchy-Riemann operator. So This was kind of routine for Gromov. But the key point will be it's compact. And that was new. Okay? So maybe I now make, when you believe this, what is written, you can now make a picture. Something like this. So here is T. Can you see it? Oh, very unfortunate.
A very beautiful picture.
Very beautiful. Shit, we have to wait 2 hours till the sun is down. Let's try. Okay, here is 0, and here is 1. And you see, so I tell you the answer. Here I paint you for every T, MT, right? And here we know, here we only have this ridiculous flat sphere, right? For the standard one, we only have this flat sphere. So just 1 point. And what you can check, it does not look like this. Something is transverse. This can be checked because the J0 is so special. So it actually looks like this. It goes out. And if you wiggle, the same will be here true. But then it can look like this. But it could also look, it's a manifold, right? It can also look like this. So if the truth is like this, we are actually very happy, right? So it's a one-dimensional manifold, and I do not say that it's transverse at every T, but it looks like this. And if there are more than one, we actually don't care. All we want to see is that it goes through. All we want to know is that at 1, there is something left. Whether there are 1 or 3 or 5, we don't care. One can prove there is 1, but then you have to orient, and it gets harder. We don't need it. We just want to know there is an odd number of solutions at 1. Then we are done. Parity, right? But there could happen something very bad in this picture. So it could be that this curve is actually like this and goes away. And then just doesn't go, it goes away, right? To some limiting T0, T star. So this would happen if you have no compactness, that the solution stopped to exist. It would still be a one-dimensional manifold. It goes a kind of away. So no contradiction to Fredholm and Sartzmail. So we have to exclude that this happens, that they go away. And this will come from a compactness theorem. The compactness theorem will imply that they must go till the end. Okay? Alexei?
Yes, it's okay.
So I want to discuss, so the Banach-Fredholm setup and the Sartzmail, I don't want to discuss. You may have seen that was done before by Uhlenbeck and Donaldson, that was known. But this compactness, this is very tricky, and that was very new. So that it cannot happen that suddenly there is nothing left because it goes away. And this is Gromov compactness theorem. And I will kind of briefly say what geometrically happens. I will not prove nothing, but just explain a picture. So something like, maybe you have to move. So I want to discuss why this is not true, right? So this non-compactness does just not happen. Okay, so, well, it's not a proof, but a discussion of compactness. Which means that this explosion does not happen, okay? So assume the disaster happens. Okay, assume not. So assume at some t star that is less than 1, suddenly nothing left. Okay? Assume that mt, now everybody's exhausted. Yeah, the black ones are dead. Shit. So mt becomes empty. At some finite t star. Okay. So well, it's this picture, t star, and unfortunately it explodes. Okay. So now we take a sequence of tks that goes there, and we try to see that we get the contradiction. So we take a sequence of tk that goes up to t star and analyze the moduli space for these tks, right? So for so we take a sequence like this, and we know that this was before, so these spaces are not empty. So for every tk, we choose there a sphere in mtk, right? So we have a sequence of spheres. These spheres are for different tks. And now Gromov proves something about such sequences. So Gromov, compactness theorem. So he says something bad can happen, but it's not so bad. So indeed, it may not converge to a sphere, but if something bad happens, all that happens is bubbling. So only the following can happen. Only SK, STK can go to, and this convergence is a bit subtle, but something like this. So what can happen is that there is a kind of a principle, a mother sphere, and suddenly there can be ears and bubbles going away. So imagine only one. So what can happen is the following. You have nice spheres, and then they start to behave like this. They start to behave a bit like this, and then a bit like this. Shit. And then suddenly like this, in the limit like this. So you can think of a geodesic that shrinks off. So this can happen, that a sphere bubbles off. And you can easily write down in examples where it does happen. Maybe not in CN, but like in CB2. So this is a very general thing. Gromov says that, we need an area bound. We need to know that there is a uniform omega-0 area bound for all over STK, but we have that because we have assumed that they all represent the same homology class, and this constrains the area, actually fixes it. This gives us the hypothesis we need, and all that can happen is that the limit sets look so ugly. So this could, of course, be because this would be bad. We are looking for an embedded or a reasonable sphere, and such a thing we may not want to have. But it's, in our situation, very easy to see that they cannot be there, just for area reasons. Let's see, let's do. So maybe this strange limit thing, this here, I call T, like tree, and this is a kind of a union of finitely many JT star spheres, right? This is a union of JT star spheres. This one, and this one, and this one, and this one. something like maybe sphere 1, da da da, sphere K. And what Gromov also proves, it comes out from his method, is that the homology class in the limit can actually not jump. So when you take these spheres and you add them up, they still represent the class C, right? So for each TK, the sphere represented this usual class, the only one we have in our S2 cross Cn minus 1. And in the limit, can one see it?
Yes.
In the limit, this is still true. But you see now, maybe I say it orally instead of writing. I don't know. Should I write? You see, the following happens. The process of Gromov says that each of them is holomorphic. So they can only be a positive multiple of the generator. Yeah, this means each of them is 0, but 1 is 1. So actually there is only 1. Because our homology class is indecomposable, right? It's a generator of the integers. So there cannot be decomposition. If you try to find holomorphic curves in indecomposable homology classes, you are in great shape because they cannot be bubbling. Okay, maybe I say that. So the point is that each subsphere each SK is holomorphic. And therefore, you see that the omega volume of such a sphere, SK, must be positive because it's a holomorphic sphere, but it must also be, well, it's this. It's homological. Maybe J. Well, it's a bit ridiculous, but so this implies that so this thing is of course homologically a certain multiple of the given only class, but this multiple must be bigger or equal than 0 because of the, it actually must be bigger than 0 because of this. Yeah, but well, in H2. Which is just said. So, and they must be integers. Yeah, but the sum is just C, right? We also know that the sum of these classes is C itself. So we see that something like after reordering S1, well, K, it means that K is 1. So it actually means that the limit object was good, so there was no problem. So no problem, we can go on. So the assumption that there was a problem is wrong. Good. Do you believe it? Kind of. I mean, I only want to give the picture. I didn't prove Gromov compactness. But I wanted to show how it's used to prove Gromov non-squeezing. Now you find for this, now you can go through in the moduli space, and for the difficult J's, you do find a sphere in the class you want, and on that guy, you repeat the proof. Great. Okay, so what's the time? Shall we give up, or shall I do one more? Now we stop now.
Yes, because in 10 minutes, we will have another talk, therefore I suggest to make a break.
Very good. So maybe I can write down a statement, 1 minute,
yes.
And you can try to prove it, exercise for next week.
Yes.
Good. So it's actually a theorem I will use for the ball packing thing. It's called Gromov two-ball theorem. And it says the following: if you have a ball and another ball, and they embed, symplectically, you look at the problem of embedding two balls into a bigger ball, so then it must be that 2a is less than a. So you should repeat the previous proof, but not in S2 cross Cn minus 1, but in Cpn, right? You should compactify this to Cpn. And then you should not work with the spheres, the flat spheres, but with CP1s, and then you get it. So this is a good exercise. Great. Okay.